Hey everybody, this is your friendly neighborhood TA Jacob. This is in the second part of the data analysis tutorial series on SPSS. And essentially what we're going to be doing today is continuing where we left off in the first part. As you recall, hopefully you're coming from the first part or you've gone to lab and have already done all your pre-processing steps. But if not, as a quick side note, please go back to that. But what we did in the first part was cleaning up our data, exporting it from Qualtrics to SPSS, and recoding our items such that they could be analyzed statistically. Okay, so one thing that I wanted to cover was how to deal with individuals who may or may not have answered honestly or maybe completely didn't do the survey at all. One thing you can do is you can click here, and what you can actually do is clear this individual. I'm not going to click here because this is my final sample, but what this does is it essentially removes the individual from your data set. Now, if you have a good N or sample size, such as 100 or more, you should be fine to do this to a couple of folks. But if an individual is only missing a couple of items, but they've answered the majority of the survey, I would personally say just to keep them in the fray. Just that way you have as much data as you need. Okay. Now, the first thing I wanted to go over was to get descriptive statistics and frequencies for our basic demographics. Now, to do this, it's pretty simple. You go up here to Analyze, then you're going to go into descriptive statistics. Now, depending on what kind of variable you're trying to analyze, in this case, I'm doing age on the left here. I'm going to click on descriptives. Now, as you can see, it's already clicked here, but what you can actually do is you could just do a point and click kind of thing, right? And once you click OK, it's going to give you the N, so the number of people who gave you their age, the minimum value, so the youngest person who took my survey was 17 years old, the oldest was 49, the average age was 21.47, so around 21 years old with a standard deviation of 3.789. These are numbers that you will have to report in your final paper. Okay. Now I'm just going to go through it again, but with nominal variables or categorical variables. Okay. So again, you go to descriptive statistics, but instead of descriptives here, you're going to go to frequencies. Now, like I said before, you can do a point click because I've done this before. You click on sex and ethnicity, so you can actually highlight them both, and you click here. It just moves the variable into this little box here, and then you click OK, and it should give you a frequency table. Now, if you kind of click back into the video, it said that to create an APA style. I did that just because it's very nice in telling you, all right, the number of males was 52, and that's 33.8%. The number of females was 99, so that's 64.3%. The number of non-binary individuals was 0.6%. And the number of people who preferred not to give away what their gender was 1.3%. And the same thing with ethnicity. Okay. I'm going to click out of this and let's get actually into our statistical analysis. If you recall, the very first thing that we wanted to assess was whether or not this test was reliable. Now, one way to do that is to get an estimate of the correlation coefficient. Actually, not correlation, reliability coefficient. And what that does is it gives you a measure of the internal consistency of your test. To do that, we're going to go into scale. So first things first, we're going to click Analyze, and we're going to click on Scale. And the first thing comes up is reliability analysis. This is what we want to do, so we're going to click on that. Now, as I said, I've done this before, so I'm just going to highlight all of my items and put them back here. But essentially what you're going to do is you're going to get all of your items, and you're going to put them in this little box here that says items. Okay. Now, if you recall, you guys probably have negatively worded items that haven't been reverse coded. Please be careful to not include that into this items box. We only want to include items that have been either positively worded or positively coded. Okay. Let's go to statistics here. What we want is the scale. So that's our reliability coefficient. And we want the scale if the item was deleted. And what this is going to do is it's going to give us an idea of what items in our test are hurting or helping our reliability. And what you can do is you can label this. So I'm going to call it reliability coefficient for uh, your name or your test name. Okay. In my case, my test name was called the Intellectual Superiority Scale, or the ISS. No, that is not the International Space Station. That is just the name of my test. So I'm going to click OK here now that everything is good. Okay. And now this is the big number that we want. This is our Chromebacks alpha, and this is the number of items. As you might notice, um, you are probably working with 10 items and not 20. This is because when I took the class a few years ago, we were required to have 20, but since then we've shortened it to only 10. So no worries, don't panic. You're doing it differently than I am. The important thing is this value here, Chromebacks alpha. That's an estimate of your internal consistency. Now, generally, we will go through this in class. You generally want it to be above zero point 0.7. So I would have acceptable reliability. Okay. And this table here is essentially giving you the Chromebacks alpha if the item was deleted. So if I deleted this item smart, which is an item that says I'm the smartest person I know, my reliability would shoot down to 0.69. Okay. And this is opposed to don't share. So this item is asking, I don't share what I know with others. If I deleted that, it would be 0.739. So maybe this item was hurting my reliability a little bit. Okay. One other thing that I would recommend doing is the nice thing about SPSS is that you can click on certain images and you can copy them. What I would recommend doing is copying things as an image and going on to a different Google Sheet. Sorry, wait for this to load. You can copy this as an image and you can actually paste it onto any document. So as we go along, I will tell you what you should paste and what you should keep. I would recommend pasting just or keeping just this image here because that's really all you need is the Chromebacks alpha. Okay. I'm going to minimize this. Okay. Now, the next thing we're going to do is to look at the linear relationships between the items. And the way we're going to do that is by doing a correlation matrix. So essentially what we'll be doing is getting all of these items and correlating them with each other and seeing if there are going to be significant relationships. To do that, we're going to click on Analyze. We're going to go down to Correlate right here and we're going to do bivariate. The reason it's bivariate is because we're only doing it between two variables. The correlation estimate is only going to be between one item and the other item. Okay, and that'll make more sense in a second. Let's just click on this, and just for the sake of demonstration, I'm going to put these all back here. Okay, we're going to highlight all of these items, or all of the items that you use to calculate your Chromebacks alpha. Remember, do not keep um, the negatively worded items, only the ones that have been transformed to be positively coded, and we're going to put them in here. If they aren't in order like mine are, you can totally just point and click and point and click. Okay. We're going to calculate a Pearson coefficient, which is essentially assuming that these are continuous variables. And that's an assumption that we make a lot in psychometrics, is that the underlying constructs that we're measuring are continuous in nature. Okay, we want a two-tailed significance test. We want to see what significant or what correlations are significant, and we only want to show the lower triangle. That way, it just makes the matrix a lot easier to see. And we're going to show the diagonal. So make sure that this is checked, the Pearson, the two-tailed is selected. Make sure you click on flag coefficients, only show the lower triangle, and show the diagonal. Once we're done that, we can click on OK. And then there it is, our correlation matrix right here. So let's just pick one correlation coefficient and see what's going on here. The diagonal is blank because if you were to correlate an item with itself, it's going to be perfectly correlated by nature. So it's assuming that it's just going to be one. That's the estimate. Now, let's look at the correlation between smart and educated. Smart is an item that asks, I am the smartest person I know, and asks whether they agree or disagree with that statement. And it's the same structure here with educated, but the question or the statement now is, I am very well educated. Now, the correlation between these is 0.15. So it's a positive correlation, but it's not strong. And the significance level, or the p-value, is 0.052. As you guys recall from your statistics class, you generally want to reach a threshold of 0.05. Now, if it's above that, you would consider that not a significant relationship. And if it's below, you would consider it a significant relationship. Now, as I said before, I would copy this as an image and put it in any document that would um, allow you to just go and refer back to these correlations because we don't want you to keep coming back to the school to just run statistics on SPSS. SPSS is already expensive as it is, and we just want to give you guys um, the experience necessary on what statistical analysis looks like. Okay, now that we're done that, we're going to do what's called a factor analysis, looking at the overall structure of our test. As you guys recall, we asked you to come up with two domains. And essentially why we wanted you to come up with two domains was because we first wanted you to create a conceptualization of what your construct was. And we wanted to get you to think about, well, what other subconstructs contribute to the existence of that construct. So one example of this could be an attitude. If we have, let's say, um, a construct of, let's say, depression, what are the behaviors or psychological processes that contribute to that construct of depression? Well, there's depressed thoughts, but there's also depressed behaviors. Individuals with depression may be um, have issues with sleep, self-confidence issues. These are all things that are um, indirectly measured by depressive behaviors and depressive thoughts. And so that's why we commonly dissociate our constructs between behaviors, external things that we do, and internal cognitive processes. Okay? All right. And what factor analysis does is it essentially looks at the correlation matrix that we made and tries to look at what beyond the variables that are being correlated here is contributing to the correlation between two items. Now, as we talked about in class, if an item is very highly correlated with another item, we assume that is because they are both measuring the same thing, or they're both loading onto the same factor. And what factor analysis does is it kind of puts this to the test and tries to put numbers to it in a way that is interpretable to us. So let's get started on that. We're going to go to analyze as we always do, and we're going to go to dimension reduction, factor. So this factor button here, we're going to click on that. And as we've already done, we're going to select all of the items that are in our test, but not including the negatively ordered items. Okay. Let's click on descriptives, or actually, let's click on extraction. The primary way that we're going to extract our factors is through principal components analysis. So let's leave that as it is. And we're going to do an unrotated factor solution. We're analyzing the correlation matrix, and we also want to see the scree plot. Okay, I would leave this as is because this is what's known as the Kaiser criterion. And we'll talk about that in a little bit. Okay. Once you've done that, let's click OK. Okay. Now, we have this column here of total, and we also have the scree plot here. What is this measuring exactly? Well, when we look at the correlation matrix of our items, what we're trying to extract are what are called eigenvalues. Now, I'm not going to go into depth of what eigenvalues are or how they're calculated, but what they represent are variables that are beyond the data that we're analyzing, but are also contributing to the covariance that we're seeing within the data. So, like I said before, the reason why two items such as this right here, oh, I think I lost it. Oh, here it is. This 0.59, that's a pretty high correlation between showing off your intellectual abilities and reminding it other individuals of your intellectual abilities. The reason why that correlates so highly is because there's likely a latent structure or a latent construct that is contributing to the presentation of these behaviors, showing off and reminding people of your intellectual abilities. You could interpret that as a behavior that is trying to gain self-validation. Okay. Now, here are the eigenvalues. And like I said before, eigenvalues try to capture this relationship that we're seeing. They try to look at the strong correlations between items um, and tries to put a number to it such that it can give us a meaningful description of what those items are measuring beyond what we're already measuring in the scale. Now, according to the Kaiser criterion, if an eigenvalue is greater than 1, then it's likely an independent factor. Okay, so now in this case, I have 7 eigenvalues that are greater than 1. I would consider that my test is measuring 7 factors, or there are 7 underlying or latent factors that are contributing to the correlation that I'm seeing in my data here. Okay. I would copy this table, so the total variance explained table, copy this table as an image and put it into a Word document. I would also copy this scree plot, copy it as an image, as we did before. And I would also copy this component matrix as an image. Now let's go over what these are. Okay. The cool thing about eigenvalues and variance in data is that eigenvalues can serve as proportions of the total amount of variance that is explained by the factor itself. So if I were to sum this all together, this would probably give me about, I want to say about 20, or it'll give me some number. I sum this all together, and I have an eigenvalue of 3.7. This is the highest eigenvalue I have. If I were to divide 3.701 by the sum of this entire column, I would get 18%. So the first factor is contributing 18% of the variance. Or another way to put it is that 18% of the variance in my data is explained by factor 1. The same thing goes with factor 2. You would divide 2.377 by the sum of this entire column, and that would give you 11.886% of the variance being explained by factor 2. And what this cumulative column does is that it adds the percentage of variance that is accounted for by the two factors together. So if I go all the way down to 7, 7 by its own only contributes 5%. But if I consider all of my 7 factors that are being indirectly measured by my scale, I find that these 7 factors contribute 63.879% of the variance in my data. Pretty interesting. Okay, let's go to the scree plot here. This is just a way of graphing the components and the eigenvalues. As you can see here, the component number is in the x-axis here, and it pretty much is limited to the number of items you have in your scale. Because if you think about it, if you have, let's say, 10 items in a scale, you can only be measuring realistically up to 10 different factors. You can't be measuring 11 factors, say, in a 10 item scale, because what would that doesn't really make sense. Can an item be measuring 2 factors? Statistically speaking, no. And on the y-axis here, we have the eigenvalue. So component number 1, we saw that has an eigenvalue of 3.7 something, and we see right here, and it's up here, And we can see that it all tapers off pretty well. This is what's called the scree plot because it's supposed to look like kind of a scree. So for those folks out there who are interested in geology or hiking, scree just refers to the buildup of sediment at the end of a cliff. So this is supposed to look like a cliff, and this kind of deflection point right here is what we're trying to look at, and we will get into that in the next coming weeks. Okay. Now, what's really cool now is the component matrix. The component matrix now looks at the correlations between the items and the factors. Right here, we have factors 1 to 7, and I have these numbers that denote my items. Okay, so smart, the correlation between smart and factor 1 is 0.432. And then the correlation between smart and factor 2 is 0.073. So we see that it correlates pretty highly with this factor 1, but not so much with factor 2. We do this for every one of the factors. And why this is very important is because this helps us identify what the factors are actually. And one easy way to kind of quickly identify what the factors are measuring is to look at what are the two highest loaders in the factor. So the way to do this is let's look at factor 1, for example. I have remind, which has a correlation of factor 1 of 0.701. That's pretty high. And a factor, or sorry, show off also measure or loads or correlates pretty highly onto factor 1 of 0.696. What do these two items have in common? Showing off and reminding people of your intellectual abilities. Well, you could reasonably argue that these are both items that are measuring the degree to which an individual is being grandiose about their intellectual abilities, the degree to which they're trying to show people or get validation that their intellectual abilities are superior. And then you do the same process for 2, 3, 4, 5, 6, and 7. That would be in my case. Now, as you may recall, you guys only conceptualized two domains. So realistically, you only wanted to see two factors emerge from your factor analysis. As I've seen, I didn't see two factors come out of this. I saw seven. Don't worry if your findings are confusing. It's a finding. A finding's a finding in my books. Okay? So that is how you do factor analysis. As I said before, let's do a quick rundown of the things that you should copy into like a document. That way you can just remember the numbers. I would copy this and, like I said, copy it as an image. I would also copy the correlation matrix. I would copy the total variance explained table, the scree plot, and the component matrix. Okay? And that's it for our statistical analysis. The next portions of the lab, we're going to be learning how to write it up. And I'm not going to go over that today, mainly just because I wanted to give a resource to people who needed to rerun their analyses outside of the classroom. But that's all I have for you today, and thanks for watching.